In the depths of space, 10 billion light-years from where we stand, there exists something that should not be possible. When scientists first calculated its properties, they checked their mathematics again and again. Certain they had made an error, they had not. What they had found was a cosmic monster that would rewrite our understanding of what nature can create. This is a journey to the edge of cosmic possibility, to a place where gravity becomes so intense that it tears apart the very fabric of space and time. We will travel backwards through time itself, racing across billions of light years to witness something from when the universe was young, when galaxies were still forming, when the cosmos was far more violent than today. The object is called Ton 618. At its heart lies a black hole containing 66 billion times the mass of our sun, compressed into a region whose boundary would extend 40 times farther than Pluto's orbit. If placed where our sun sits, it shines with the luminosity of 140 trillion suns, making it one of the brightest objects in the universe. Despite the 10 billion years, its light has traveled to reach us. When this light began its journey, Earth did not exist. The sun had not yet formed. The universe was barely a quarter of its current age. Let us begin that band of light. Stretching across our nicked sky is the Milky Way, our home galaxy can containing hundreds of billions of stars. Somewhere within lies Sagittarius, a star, a supermassive black hole containing 4 million solar masses that anchors our entire galaxy's rotation. By any normal standard, it is enormous, but what we seek is 16,000 times more massive. Our destination is not in this galaxy, not even close. To reach it, we must leave behind every star, visible to the naked eye, push beyond the local group of galaxies, beyond the Virgo supercluster, beyond everything familiar. We must break the cosmic speed limit itself. As we accelerate past light speed in this thought experiment, the Milky Way shrinks behind us. Its spiral structure becomes clear, revealing graceful curved arms, dark dust lanes, bright star-forming regions scattered throughout the disk. Soon other galaxies appear, the large and small Magellanic Clouds, our satellite galaxies, then Andromeda, our nearest large spiral neighbor containing perhaps a trillion stars approaching us for a collision in 4 billion years. We push outward. More galaxies emerge. Dozens, hundreds, thousands. Each contains hundreds of billions of stars. Each star might have planets. Each planet might harbor life. Yet we have never detected a signal from another civilization. Perhaps we are alone. Or perhaps the universe is so vast that civilizations simply cannot find each other across the cosmic void. Now we enter true intergalactic space regions, so empty you could travel millions of light years without encountering a single star. The temperature here is just above absolute zero, warmed only by the faint afterglow of the Big Bang itself, but darkness does not last. Points of light begin to emerge, scattered at first, then multiplying until they fill every direction. Galaxies, thousands upon thousands. These galaxies are not randomly distributed, but organized into vast cosmic webs, sheets and filaments separated by enormous voids. This is the large-scale structure of the universe, carved by gravity over billions of years, as matter flowed along invisible rivers of dark matter, clustering into dense knots and leaving vast empty spaces between. As we travel farther, looking deeper into cosmic time, the galaxies change character. Nearby galaxies are mostly mature systems with orderly rotation and reduced star formation. But as we push back in time, galaxies become younger, more irregular, more active. We see more vigorous star formation, more evidence of mergers and interactions. This makes sense when we look at distant objects. We see them, not as they are now, but as they were when their light left them. Light from a galaxy 10 billion light-years away shows us that galaxy as it existed 10 billion years ago. We are literally watching cosmic history unfold ahead. One point of light grows brighter than the rest. This is no ordinary galaxy. This is a quasar, a beacon shining across cosmic distances, with power beyond imagination. When these objects were first discovered in the early 1960s, astronomers thought they were seeing strange stars in our own galaxy. They appeared as points of light, showing no structure, even in powerful telescopes. But when astronomers analyzed their spectra measuring the characteristic fingerprints of different elements, they found something impossible. The spectral lines were shifted dramatically toward longer, redder wavelengths, indicating these objects were receding at tremendous velocities, often 10% or more of light speed, according to Hubble's law relating velocity to distance. In an expanding universe, this meant these objects were billions of light years away. If visible at such distances, they had to be incredibly luminous, more luminous than entire galaxies, containing hundreds of billions of stars. Yet they appeared as points, suggesting all this energy came from regions no larger than our solar system. The energy density was higher than anything previously encountered. The answer, which became clear through the 1960s and 70s, were supermassive black holes, consuming enormous quantities of matter. As material spirals inward through accretion disks, heating through friction and magnetic interactions, it radiates vast amounts of energy before crossing the event horizon. This particular quasar, designated TUN 618, was first catalogued at the Tonantzintla Observatory in Mexico in 1957. For decades, it remained largely ignored. One more blue point among thousands in a stellar survey. But as technology improved, astronomers realized this was exceptional. The black hole at its heart was not just massive, but ultramassive, one of the largest ever discovered. As we approach, the quasar resolves from a point to a disk, then to a vast churning maelstrom. We are now close enough to see the components that make this object shine so brilliantly. Across the cosmos, surrounding the black hole, extends an accretion disk spanning thousands of astronomical units, a swirling vortex of doomed matter. This disk has distinct regions with dramatically different properties. In the outermost regions, far from the black hole's strongest influence, the disk resembles a slowly rotating gas cloud. Temperatures are relatively cool, a few thousand degrees, comparable to red dwarf surfaces. Material orbits at a few hundred kilometers per second. The gas is still mostly neutral, not yet ionized. Moving inward, conditions intensify. Gravitational pull strengthens, and orbital velocities increase. At a few hundred astronomical units from the center, material orbits at thousands of kilometers per second. Friction becomes intense as different parts of the disk orbit at different speeds. Faster inner material rubs against slower outer material, converting orbital kinetic energy into heat. Temperatures climb to hundreds of thousands of degrees, then millions. The gas becomes fully ionized, plasma-free electrons and bare atomic nuclei. This plasma is threaded with magnetic field lines generated by charged particle motion and amplified by dynamo processes. These fields are crucial. They transport angular momentum outward through the disk, allowing material to lose energy and spiral inward. Without this mechanism, material would simply orbit indefinitely, unable to fall toward the black hole. The magnetic fields also create chaos. They tangle and twist, building up energy periodically, released in flares and eruptions. Through magnetic reconnection events, the disk is not smooth and orderly but violent and turbulent, plasma churning under gravity pressure, and electromagnetic forces in the innermost regions. Within a few astronomical units, conditions become truly extreme. Temperatures exceed billions of degrees, hotter than stellar cores, hotter than anything in nature except, perhaps, the moments after the Big Bang, or during neutron star collisions. Material moves at 30 to 50% of light speed. Relativistic effects become important: time dilation, length contraction, frame dragging from the rotating black hole. All play roles. This innermost region is the innermost stable circular orbit, the closest distance where matter can orbit without falling in. Its exact radius depends on black hole spin. For a non-rotating black hole, it sits at 3 times the event horizon radius. For a maximally rotating one, much closer, at just over 1 event horizon radius. Material here is on the edge of doom. Any slight perturbation sends it spiraling across the event horizon within hours or days. This is where accretion efficiency peaks. Material has fallen through most of the gravitational potential, reached maximum velocities and temperatures, and radiates at maximum rates. This innermost region contributes disproportionately to total luminosity despite occupying small volume.